Hey everyone, welcome back to Code in Motion. Today we're looking at LeetCode problem number 338, counting bits. So given an integer n, return an array of length n plus 1, such that for each I between 0 and n, the answer at I is the number of ones in the binary representation of the number. So let's take a look at this example. N is equal to 2. So we're going to return back an array of length n plus 1, in this case 3. And we're going to want to return back the number of ones in the binary representation for 0, for 1, and for 2. So 0 is just 0. It has no ones. That's why we return back 0. 1 in binary is just 1. It has 1, 1. That's why we return back 1. And 2 is 1, 0. It only has 1, 1. So we return back 1 as well. So we're going to be using dynamic programming for this solution. And you should really think about dynamic programming where the question asks you to return back an array of numbers, an array of results. And it seems like you could find a pattern where the number or the result at index I in the result array depends on the result of a previous index, right? And so dynamic programming is an optimization in order to use previous results to collect your current result. And so if we didn't use dynamic programming, the brute force way would be basically to count the number of 1 bits for every single number between 0 to n. However, we could perform a much more efficient algorithm if we only calculate the number of ones for 0, and then for the next numbers, we use the result of the previous numbers. And that's the concept of dynamic programming. And so on the left-hand side, I have just binary numbers 0, 0, 0 all the way up to 1, 1, 1. And on the right-hand side, I have the dynamic programming array that's going to keep track of the previous results. And so what we're going to do first is we're going to initialize dp of 0 to be 0, and then we're going to start at index 1. So why is dp 0 equal to 0? Well, it's because the binary representation of 0 is just 0, 0, 0, and it has no ones, right? So that's our kind of like our base case. So dp of 0 is 0, and now let's start at index 1. So let's highlight this. And now I'm going to process the binary number 0, 0, 1, which is 1. And something to note over here is that 0, 0, 1, so 1 is an odd number, right? And what does that mean if you're in binary representation and you're an odd number? It means your rightmost bit, in this case the least significant bit, is always going to be 1. Right? That's what it means to be odd in binary. If you're even, then the rightmost bit is going to be 0. And so let's think about this. If we're odd, that means the rightmost bit is 1. That means you could just check the previous bit string, which is even, and you know you have to add 1 to it. So your answer is going to be what the answer was for the previous bit string plus 1, right? So in this case, since 1 is odd, we're going to look at dp of 0, and we're going to simply add 1 to that result. That's how we're going to use the previous results to our advantage. So if we're odd, we're going to say dpi is equal to 1 plus dpi minus 1. That's going to be the formula we use for odd numbers. So let's update that to 1. And now let's move on to the next element. Now in this case, we're processing 2, which is 0, 1, 0. Now this is an even number, right? And so how do we calculate the number of ones for an even number? Well, what do you realize? 0, 1, 0 is actually just 0, 0, 1, but shifted over by 1, right? So anytime we deal with an even number, you could just essentially look at the bit string that's shifted over 1 to the right, and you're going to have the same exact number of ones as that bit string. So essentially, you're looking at the current number divided by 2, and that bit string will have the same exact number of ones because we're just shifting the ones from left to right, but the number of ones stay the same. And you'll see this that 0, 1, 0 has the same ones as 0, 0, 1. And so if the number we're looking at is even, we're going to check for the number of ones of I shifted over to the right by 1. Okay, and so in this case, 0, 1, 0 shifted over to the right by 1 is just 0, 0, 1. So what is dp of 0, 0, 1? It's actually 1. And so we're going to copy that answer. And so if the number we're scanning is even, dp of I is equal to dp of I shifted over by 1. And these are the two cases, right? You could either be even or odd. And this is the formula we're going to use to calculate the rest. So let's go to 0, 1, 1. 0, 1, 1 is odd. So we need to check the result from the previous bit string, which in this case is 0, 1, 1 minus 1, which is 0, 1, 0. Now we know since we're odd, we're going to have one more 1 than the previous even number, right? And so dp of 3 is equal to 1 plus dp of 2. In this case, it's 2. Now we move on to 1, 0, 0. This is even, right? This is the number 4. So we know that this has the same amount of 1s as the bit string that's shifted over 1 to the right, right? All we're doing is shifting 1s, but the number of 1s stay the same. And so dp of 4 is equal to dp of 2, which is 1. Now we go to 1, 0, 1. This is odd. So we look at the previous dp result, and we're going to add 1 to that. So 100 had 1, 1. Now we have 2 1s for 1, 0, 1. And now we go on to 1, 1, 0. 1, 1, 0 is even, so we're going to look at the bit string that's shifted over to the right by 1. So we're looking at 0, 1, 1, which is dp of 3. And so dp of 6 is equal to dp of 3, which is 2. Now the last element is 1, 1, 1, which is odd. So look at the previous result and simply add 1 to it. In this case, it's 3. And we're done the algorithm. Our dp array is actually the result array that we're going to return at the end of the algorithm. It stores the amount of 1s for every single number. And this algorithm runs in O of n time because we iterate through all the numbers from 0 to n. And it has O of n space complexity because we store the results of all the previous numbers. So let's code out the solution now. So we know we need the dp array. So this is going to be 0 times n plus 1 because we want to go through 0 all the way to n. So we use n plus 1 for the array length. Now for I in range, we're going to start at 1 and go all the way up to len dp. We start at 1 because we know 0 has 0 1s. That's the base case, right? So we start at 1. And now we're going to say if I is even, so if I percent 2 is equal to 0, so if I is even, we said that dp of I is equal to dp of I shifted over to the right by 1. Else, this means it's odd. So dpi is equal to 1 plus dp of I minus 1, the result of the previous element that's even plus 1 to that. Now we just return the dp array and we're done. Let's run this. And it succeeds. Thank you so much for watching. If you're interested in more content like this, be sure to subscribe, and I'll see you in the next one.